Hi, welcome back. Today we're going to talk about wildlife populations. This is Save the Wild Chinchillas. This is technically our lecture 3 if you're going in order. I'm actually recording this as like a second, so I'm not going in order. You don't have to either. Feel free to skip around, look at what you like, and enjoy it. So this is our lecture on wildlife populations. Once again, ZGAP and Tulsa Zoo are the ones that are that paid for these videos to be made and produced and distributed. They do this for wildlife projects all over the earth, not just my chinchilla project in Chile. We're a small little part of what they do to support conservation throughout the world. So wildlife populations, let's see if I can figure out how to make this go away real fast. We want to talk about how do we define a population? Where are the boundaries? Are we looking at one little area, or are we looking at the worldwide distribution of something, the entire worldwide distribution of the animal, or a local area for a population? So I see the chinchillas and Alcoa as one population in this local area on these mountains. This is a 3D representation of the mountains. The National Chinchilla Reserve is right here. And these animals, it's reasonable to think that an animal from over here could reach an animal over here because the area is not that big for breeding. So for genetic exchange between animals, that's how I define how a population should be. So for me, this is the population in Alco, Chile. There's another population hundreds of kilometers further north, which a chinchilla, the furthest one that's traveled in a night, is 250 about meters. There's no way it's going to travel from here. It's highly unlikely, all the way up 250 kilometers further north to another area where there's chinchillas for breeding purposes. So a population, the sum of all individuals of the same species in a common area. We have annual trends in population. So annual population trends and annual cycles refer to the population trends on a yearly basis, the births and deaths within a year. Population levels are highest after the breeding season because that's when you have all the birth, right? And those higher populations usually coincide when there's food available. So it's spring and summer, when there's abundant resources. And it results in a brief natality season or a brief birthing season. The young that are born at periods of lower resources are more susceptible to mortality. There's less resources, or there's less food for them. Lower populations are just before the breeding season in the fall and the winter, and that's when the resources are the scarce. So this coincides, your population trend coincides with the available resources and food. Now, the chinchilla populations exist in a Mediterranean climate, the long-tailed chinchillas. The short-tailed chinchillas, you can even say in a desert one for a little bit further north. And these are the wet winter seasons. So food resources, green grasses, annuals, are the highest during just after the rains. And sometimes those begin in May. And so we'll have green grass by June. And sometimes we won't have it for 4 or 5 years, depending on the drought. And reproduction will begin just after the onset of the rainfall, reproductive activities. Because for rodents, we believe that the ingestion of green vegetation, green grass, the chinchilla's preferred food is the grasses in the area, induces reproductive response. Density is the number of individuals per an area. So for chinchillas, we say so many animals per a unit area, per hectare, because we measure in hectares down there in Chile. Data is useful if you have 2 different sample periods or 2 different times of the year. So if you take the density of the animals during the spring and then the density of them during the winter, you're going to see that you're going to have more animals per hectare, 2.4 during the spring, we'll say, and 1.7 during the winter. Those numbers are not exact examples. I just pulled these numbers out of my brains. I think that's 2.4 maybe is the average for chinchillas per hectare. This data is used to detect changes in populations, trends, cycles, and patterns. So we can see if a population is growing or declining. But for that, we want to use data from the sample periods, 2 different sample periods from 2 different years, but the same season. We don't want to compare spring of one year to winter 3 years later and say, oh, our population is declining. Well, of course it's going to be declining because you're going to have a lower population if you take the sample during winter. If you look at that population during a winter compared to a spring. Biomass is another way that people are biologist people, used to compare species densities, but it's density times their average weight of a species. So if we have, say, a chinchilla, there's 2 chinchillas per hectare, and there's the weight of the species 500, that's going to be 1,000 grams, is going to be our biomass for the area. Now, this is used to compare populations of different species. So we could compare chinchillas to, say, some other animal. We look at its density, we'll say it's 2, and their average weight's 100. That's going to be 200 for the area. And I did that math wrong for the chinchilla one. But anyways, you get the point. This is used, biomass is used to compare how much of a species is in one area compared to another species. And the only way to do that is to use this biomass formula, because you can't compare 2.4 hectares for chinchillas if you to 5 hectares or 5 animals of pumas per 28 million kilometers, however their home range sizes. I don't know it exactly, but anyways, biomass is used to compare populations of different species. So to understand populations, we need to look at the parameters in populations, and that's the number of individuals. How many individuals are living in that area, in that population? Their rate of increase or decrease, their rate of reproduction, and the rate of loss or mortality. And we need to look at population structures. This is age and sex. So normally on these curves, we'll have female and male, and it'll, I'm not sure which side is which usually, but so what we have here is an expanding population. It's in the shape of a pyramid. So there's a lot more young. These are the young ones, and it goes up in age, and these are the old people. So there's a lot more being born than dying, and that's an expanding population. Here we have a stable population. It looks more squarish. You have about the same amount in the lower age groups as you do in the higher age groups. And then in a declining population, you're going to see a lot less young than old. And so that would be a declining population. Natality. So when we talk natality, we're talking about the litter size. How many are born in that litter? The number of litters per year. Are you having 1 litter per year, 1 litter a month, 1 litter every 3 years, depending on the reproductive characteristics of the animals? The minimum and maximum age of reproduction. That's the time of an animal's able to reproduce. Sex ratio and mating habits. If you have a 50-50 sex ratio, you're having a monogamous couple, a female and a male mating. If you have 3 females to 1 male, then that male, it's not monogamous, obviously. You have 1 male to 3 females. His home range probably overlaps that of 3 females. And so he's got a larger range, and it overlaps these 3 females. That's the sex ratio and mating habits for different populations different. And population density, how hard is it to find a mate? How sparse is your habits? You know, how sparse is the habitat where you can live, and how far away are possible or potential mates in that area? So for chinchillas, here we're going to have an original mated pair, a mother and a father. The first offspring will be the replacement of the mother. We've not had any population growth yet. The second offspring will be the replacement of the father, if these offspring live to reproductive age. So recruitment or population growth is only achieved after the replacement of the parents. So offspring number 3. So for chinchillas, this probably isn't going to happen until the second year of this mated couple, because in the first year, they may have 1 or 2 offspring. It might take more years before we see any kind of population growth. And so this is slow. These are K-type species like elephants. They have a small litter size, not very many litters per year, 1 or 2. They have 1 or 2 in their litter, 1 or 2 litters per year. The minimum age of reproduction for a chinchilla is going to be from the day of conception to the day that chinchilla can start breeding is about a year, actually. The sex ratio is 50-50. So are you going to be able to find a mate? Those are natality things. So we just went over this in detail for the chinchilla. 111 days is gestation. Here's chinchilla. Here's what we're looking at, the type of rodents, a caviomorph gestation. These are in the parentheses are different sources of the data. So for a long-tailed chinchilla, 111 days, it's 118 for short-tailed chinchillas. The litter size is 1 or 2 offspring. The age of first reproduction is 8 months, but they already have had 3 months gestation. So it's about a year since conception that the animal is going to be able to be reproductively active and maybe reproduce. Litters per year, they only have 1 or 2. Now, if we look over here at Phyllodes darwini, this is Phyllodes darwini. So that's the chinchilla's Phyllodes darwini. This is Abercombe bonetti, cute little rat. And these are Octodon degus. Those are scientific names for these animals. So degus, chinchilla rat, Abercombe bonetti. Phyllodes darwini is the leaf-eared. Darwin's leaf-eared mouse. So this is what we're going to look at. Now, it's a different type. It's not a caviomorph rodent like the chinchilla. It's a different type of rodent. Its gestation is 1 month, about a little bit more than 1 month. Its litter size is 2 to 7. Its age of first reproduction is 1 month. It can have multiple litters per year, and it's distributed actually. So the chinchilla's only in the chinchilla, long-tailed chinchilla's only in Chile. The short, or the Darwin's leaf-eared mouse is in Argentina, Chile, and Peru. So it's got a bigger range. We'll talk more about this in a minute. Dispersal. So this is when an animal leaves its natal group. And so here we have a female chinchilla. We know she's the mother of this offspring and one other. He was the first. This is a male. He was born in the first litter of hers in 2016, so about May. And you can see that she's got these lactation marks, and she's got a little, you can't see him, he's over off the side here. She's got a little baby. He's about, let's see, he's about a month old in this. So when her second offspring of the year, in her second litter of the year, she's lactating, he's nursing, she's chasing off this one that's about maybe 6 months old, 8 months old. This one's reaching sexual maturity. She needs to get him away from her. She needs to spend all of her resources on trying to take care of her new offspring. We believe the females stay in their natal colonies. Mortality. Older ages are reached in captivity because you have protection. The animals have the resources they need. They have water, food, they have medical care, they have shelter. This stuff is not guaranteed out in the wild. So you'll see older chinchillas living to be 30 years old, between 20 and 30 years old in captivity. That's not in the wild. In the wild, we think it's about 7 years. Another mortality factor is predation, predators, and the predator and prey relationship. We'll talk about this on another slide. And parasites. This is a ventuca. They suck your blood. That's not the problem. The problem is when they walk on your finger, as they are here on this person's hand, they're leaving little pieces of fecal material. In that fecal material is a parasite. It causes the disease Chagas, which Darwin is to believe to, I think he was believed to, he had, and maybe it caused its death. Anyways, they'll bite you. That's okay. It doesn't matter. Wash your hands really well. Because what you don't want to scratch, because once you scratch, then you're getting that fecal material with the parasite in it into your bloodstream. And that's how that parasite works. Now, parasites do not decimate an entire population. Otherwise, they wouldn't have food. So they're going to take out some of the population, but not all of it. Another mortality rate is poisons like DDT and bird eggs. So birds of prey in the 70s got DDT into the system from eating, I guess, rats maybe that were poisoned by it. I don't know the specifics. It doesn't matter. What matters, I mean, sure, I'm sure it did matter, but the specifics don't matter. What matters is poisons can affect birds in ways we didn't know. And what happened was the calcium and the structure of the eggshells, when the eggs went to sit on the shells, or when the birds went to sit on the eggs to incubate them, they would crack. They would just crack. So we saw a huge decline in birds of prey. And they're just now, some of those populations are just now coming back up. Unfortunately, DDT is still manufactured and sold, or some form of it is, in Chile, although it's not legal in the US. Another mortality is accidents. The young, sometimes they just fall. They don't have experience. They don't know not to go to this place, not to do that. They don't have the experience, and they're going through the learning process from their from their parents, hopefully, if they have that kind of structure where parents invest a lot of time and energy into their offspring. So accidents, young, starvation, climate, we're in a drought. We normally would have about, I want to say 100 millimeters of rain by now. In Chile, we've had 28 this year. So, and it's an ongoing drought. It's been going on for years. So that affects the seeds, the plants, the vegetation, and that can lead to starvation. So that's a mortality factor. And then another one is stress, and that's density dependent. So density dependent, at higher populations, you have higher mortality. There's compensatory actions. If predation is reduced, disease or other biological factor will usually come and keep a population in check. So say all of the predators are killed and because they're hunting those, then disease or some other biological check will normally keep a population at a stable level, and you won't see that as much density. It'll bring it so the density dependent is in check. Density independent mortality. Now, this is not related to the number of individuals in a population. Density dependent is how many animals are in that area. If you throw 20 chinchillas in a little area in a cage, you're going to have some stress factors and some fights, and you're going to have some disease probably or something that's going to increase some mortality. Density independent doesn't matter how many individuals are in the area. These are wildfires, landslides, flooding, flash floods, and these are not related to the number of individuals in the area. It's something outside of that. Biotic potential is achieved when there's abundant resources, birth rates are high, and biomass production at or near maximum. So you're having a lot of offspring born as much as possible, really. And that's because there's lots of resources. So you're having those high birth rates. I'm not going to go over this logistical S-shaped curve, not for this. It's maybe I won't. Let me look and think. Well, I'll just do it real fast. So this is in fish, not in birds or mammals. So, but we care about these other animals. So small populations will achieve higher populations slowly at first, and then a steep increase until the population reaches a level. Then some decimating factors increase with the population. So something that's going to make that population go down until there's a point where they're in check. And this is when there's enough resources for the population, and the limit for the area for the resources is the carrying capacity. How much of this area how much resources can support how many animals, and that's the K level, carrying capacity. Exponential growth, or J-shaped curves. Now, this is biotic potential is reached until some point when the carrying capacity of the area is approached or reached without density dependent mortality factors, decreases, or environmental resistance. So what happens is, I hope we go to, we aren't going there yet, so never mind. So what you'll see is a sharp increase in the population, and Phyllodes darwini, these Darwin leaf-eared mice do this. The chinchillas can't reproduce fast enough for this to happen for them, for a J-shaped curve. Maximum growth rate is the biological potential. How fast can the animals grow? The turnover rate is the replacement of old by young, or death by birth. Stability in a turnover rate is when the births are about equal to the deaths. That makes sense. You're staying stable. Here's a little note on productivity. Secondary productivity is the rate that new animal biomass is added to an ecosystem. And that means primary productivity is always plants, sun energy to plants that's making that's primary productivity. Secondary productivity is that new animal biomass is added to an ecosystem, new through birth. Leopold describes 3 types of populations: a stable one, you see little fluctuation from year to year, an eruptive one with these J-shaped curves, and that's that Darwin's mouse. And I think maybe the next slide has what we want to talk about with that. And then you have cyclic populations, and these go from high to low periods at regular intervals, and the prey species will go up, and then you'll have a lag period, and the predator species will go up, and they'll go up and down, and these are in different cycles depending on the species. So for the lynx and the hare, it's about a 10-year cycle. Eruptive populations occur in R-type species. These are species that reach sexual maturity at a young age. They have large numbers of litters and large litter sizes. And for us, it's this Phyllodes darwini. So after El Nino, after we get lots of rain in our ecosystem, El Nino is a oceanic atmospheric condition where we end up with lots of rain in our Mediterranean climate during the winter, because it's a Mediterranean climate. And that leads to lots of seeds being produced, lots of grass being produced, lots of resources. Now these Phyllodes darwinis, where is the chart? Let me find the chart real fast. Let's go back to it. Phyllodes darwini. Here he is. Gestation is 34 days, a month. So it's pregnant for a month. The babies are born, and then a month later, they can reach sexual maturity, and they're having 2 to 7 offspring at a time with multiple litters at a time, or not at a time, in a year. That's why these Phyllodes darwinis, let's get back to where we were, sorry about that, have an eruptive population, these J-curve fluctuations in their population. Then they're going to die down once all those resources are gone and there's no resources left. Right now, we're in this drought, so there's not going to be as many Phyllodes darwini by far as there are after an El Nino event. Cyclic populations vary on a regular interval. El Nino, these JK ones are eruptive. It's not on a regular interval. The hare and the lynx are up and down at a regular interval. I'm thinking that's that might be a picture of a hare from our station, not one in the Arctic where the lynxes are, or the subarctic. Stable populations are due to a stable environment, and populations return to about the same level. Eruptive are those R-type species. Chinchillas are K-type species like elephants. And cyclotic rabbits, the hares, the lemmings, and the voles, they're on a 3 to 4 year cycle, and the predator population follows or is influenced by the prey cycles. Thank you. That is our introduction to wildlife populations.